Hello, my name is Curtis Struble, and I am presenting for Team 1. This is our project, What the Flip. It is an analysis on how the chamfer depth and angle of a coin will affect the flip outcome. So the probability of a coin landing on either heads or tails is normally 50%. This is why it's used in many everyday decisions. We can see here's a pretty good example of one being used in sports. Now, for some reason, if you wanted to rig that coin or bias it, you would change the center of mass, and it would land on whichever side would be heaviest. However, we wanted to investigate how changing the geometry of the coin would affect which side it would land on. Our experimental objective was to change the chamfer angle and depth on one side of a coin to study the effects on which side that coin would land on. And then further, we wanted to see if there was a relationship between the amount that we changed the chamfer angle and depth and the frequency that it would land on a certain side. Now, our null hypothesis is that the more we change the chamfer angle and chamfer depth on a coin, the more skewed the data will be towards one side or the other of the coin during the coin flip. Our experimental setup, we 3D printed 8 coins from PLA plastic. All coins had initial dimensions of 25 millimeters diameter and 5 millimeter thickness. We had one control coin, and then we had 2 altered geometry families. The first one was chamfer angle. We had 30 degrees, 45 degrees, and 60 degrees. The second was chamfer depth. We had 1, 2, 3, and 4 millimeter chamfer depths on that family. And then here are the physical coins after printing. Each of them are labeled. For our basic data collection techniques, each coin was flipped by each group member 50 times. Then after each flip, the side that was facing up was recorded, and heads was the altered side, tails was the unaltered side. You can see here in this picture that heads is marked in a black marker on the face up side of the coin. So to analyze the data that we took, and I believe we had around 4,000 data points, we performed 2 types of tests to verify 2 hypotheses. We used a t-test in order to examine if the means of each coin deviates from the expected mean, and then an ANOVA test in order to determine if there's independency between factor levels and the mean. So here is our code for the ANOVA test. You can see we have several different data packages, each from each group member. And then on the right side, you can see where we actually ran the test. MATLAB has a really nice built-in function for that, so we just went with that rather than R. And here are the results. So both ANOVA analyses were single-factor tests for variance. This was because we only chose to change any given coin with either angle or depth. We didn't do both. So the results manifested no evidence suggesting a relationship between different depth or chamfers with the probability of landing on heads. So our initial hypothesis was incorrect. Neither the angle or chamfer depth significantly altered the mean probability overall. Now we carried out a t-test to kind of look more specifically at each of those steps as far as our altered geometry of the coin. So you can see here again is our t-test code. Again, MATLAB was super useful for this, super easy. And then here are our results. Now, we had an expected mean of 0.5, but we also used a experimental mean from our control coin. I'll go into a little bit more detail on why we used a control mean later on. But the control mean was 0.514, 51.4% chance. So our H0 is that the means of the coin group will equal the expected mean, whether that is the 0.5 or 0.514. Now, our table here shows, this is directly from MATLAB, a 1 will mean reject null hypothesis, a 0 will mean to accept it. So this table is really nice because you can really visualize the effects of each family and each step size within the family of effect. So our control obviously is 0, so we're gonna accept the null hypothesis. And we can actually see with our expected average mean of 0.5, only the most extreme chamfer depth and chamfer angle will actually make the coin deviate from that mean to any significance. Now, using our experimental mean of 0.514, only the chamfer depth of 4 millimeters had an effect. From this, we can kind of state that the chamfer depth has more effect than the chamfer angle, actually. So in conclusion, at the beginning of the experiment, we were wanting to determine whether or not putting chamfer on a coin will affect this flip statistics. Our original hypothesis was that not only would changing the chamfer depth and angle skew the data, but there would be a relationship between chamfer levels and skew amount, ideally either linear or exponential. But according to the collected data and the results of our T and ANOVA tests, our original hypothesis was incorrect. Instead, it seems that there's a threshold in which our chamfer significantly affected the flip statistics. So if you remain below that threshold of 4 millimeters on our experimental mean, then there would be no effect on the original mean of the flip statistics. Now, some of the problems we encountered: the way we printed the coins gave them an uneven distributed mass. This was because the bottom layer thickness of the print was a little bit thicker than the top. Human error was another factor. This was due to kind of the definitions of a quote-unquote clean flip, whether or not that bounced off of physical objects on a table, and etc. The third was our step size. There might be more space for a little bit, maybe more resolution in our step size, and we might find a better relationship between altered geometry and probability, but that is outside of our current experiment. Now, how we attempted to alleviate these problems, we had our control coin. We used that as kind of a test to see how much that uneven mass distribution would really affect the ideal mean of our coins. And as I stated before, our mean was around 0.514. Now, we took this as within acceptable limits and continued the experiment as before. We also increased our total flips per coin to 500 during our data collection. And if we were to conduct this experiment again, the way that we would mitigate these errors a little bit more would be to print the coins at 100% infill, create a flipping rubric to better define what a good coin flip would be, and then using more intermediate factor levels, so maybe using a step size of 0.5 or even 0.25 millimeters for chamfer depth, and then maybe a step size of 5 degrees for chamfer angle. Thank you for watching our presentation, and thank you for your time.